Hi everyone, today we're continuing chapter 18. So today we're going to discuss how to calculate an entropy change for a reaction using standard entropies. So just as a review, to calculate standard changes in entropy or in enthalpy or even in Gibbs free energy, for instance, we need to use standard states. So you might remember that the standard state is the state of a material at a defined set of conditions. So the standard state for a gas would be a pressure of 1 atmosphere. For a liquid or a solid, the standard state is a pure substance in its most stable form at exactly 1 atmosphere of pressure, and then usually 25 degrees Celsius. And then for a solution, the standard state is a substance in a solution with a concentration of 1 mole per liter. So in your textbook, in the very back, in one of the appendices, there's a list of standard entropies for different molecules. Now, if we want to calculate the standard molar entropy for a reaction, we need the standard molar entropy of the products, and then we'll subtract the standard molar entropies of the reactants. Now, standard molar entropy is an extensive property, which means that it depends on the amount. So, for instance, mass changes depending on the amount of a substance, volume changes based on the amount of a substance. So those are extensive properties as well. So molar entropy is also an extensive property. It depends on the amount. Now there's also intensive properties. So density, for instance. Density depends on mass and volume. But density of a substance doesn't change based on the amount because it's always a ratio between mass and volume. All right, so standard molar entropy values are for 1 mole of substance at 298 Kelvin, so 25 degrees Celsius, for a particular state, a particular allotrope, a particular molecular complexity, etc., etc. So the standard here is that we have 1 mole of substance at 298 Kelvin. All right, now let's focus a little bit on the third law of thermodynamics. And earlier we said that the third law of thermodynamics tells us that the entropy for a perfect crystal at 0 Kelvin is 0. So we call this the absolute entropy. All right, now what this tells us is that if we have a substance at a temperature above 0 Kelvin, then it will have some amount of entropy. So at absolute 0 or 0 Kelvin, we're assuming that molecules don't have entropy because they're in a fixed rigid state. They'll be frozen at that temperature. However, not everything is going to form what we call a perfect crystal at 0 Kelvin. So a substance that isn't a perfect crystal at absolute 0 does have some energy from entropy. But we're typically considering temperatures above 0 Kelvin, so just keep in mind that the absolute entropy of substances is always positive. Now, in your textbook, there's a table summarizing some standard molar entropy values at 25 degrees Celsius or 298 Kelvin. So again, you'll notice that all of these entropy values are above 0, so they're all positive. Now, the reason we're emphasizing this is you might recall that in a previous chapter when we were discussing enthalpy, certain substances had an enthalpy of 0. But that's not true here for standard molar entropies at reasonable temperatures. So at temperatures above 0 K, the molar entropy or standard molar entropy will always be greater than 0. Now you might also notice that there's variation here in terms of the standard molar entropy. So for instance, water as a liquid has a standard molar entropy of 70 joules per mole Kelvin. But then let's see, if we compare that to a gas, like let's just say water as a gas, that's an easy comparison, you'll notice that the standard molar entropy has increased. And this does follow what we said previously, that gases have more entropy than liquids. But then even within the gases, you'll notice that there's some variation. So H2O gas has a standard molar entropy of 188.8, but then ethene down below has a standard molar entropy of 219.3. So why do the standard molar entropy values change for different molecules in the same state? Additionally, if we look at the solids, so let's compare sodium, which is just by itself, so it's a pure substance. That has a standard molar entropy of 51.3. But then if we compare that to potassium, potassium has a greater standard molar entropy. Why is that? And then if we look at iron 3 chloride, that has a standard molar entropy of 142.3. So that's much greater than the standard molar entropies of sodium and potassium. So why? Why are these all different? So again, it has to do with states. So the gas state does have much larger entropy than the liquid state if you're comparing them at the same temperature. But then also the liquid state has a larger entropy than the solid state. So if you're comparing the same molecule in different states, the state will have an effect on entropy, as we've said before. So on the last slide, we already compared liquid water to gaseous water, and we saw that the entropy of the gas was much greater than that of the liquid. But another factor that affects standard entropies is molar mass. So remember, we looked at sodium and potassium had a larger molar entropy than sodium. And that's because potassium has a larger molar mass. So the larger the molar mass, the larger the entropy. So if we look off to the right and compare the noble gases, we can see that helium has the smallest molar mass out of the noble gases. Xenon has the largest molar mass. Now also helium has the smallest standard molar entropy of 126.2, and xenon has the largest standard molar entropy of 169.4. So the reasoning behind this is a little beyond where we're at in chemistry, but in general, heavier atoms will be closer to each other in the gas state because they are so large, and that's going to allow more dispersal of energy. All right, now another factor that affects standard entropies are what we call allotropes. So allotropes are substances that are composed of the same thing, but just have different structures. So down below, we're comparing pure carbon, but in one form we have diamond, and in the other form we have graphite. So there's just different structures of carbon there. So they're allotropes of each other. So the less constrained the structure of an allotrope is, the larger its entropy. So if we look at graphite, you might remember from a long time ago, we were comparing diamond to graphite, and we said that graphite actually has sheets. So that's why we use graphite in our pencils, because as we write, sheets of carbon come off of that molecule or that structure. But then in diamond, everything is tightly bonded together. So all of those carbon atoms are rigid and extremely structured. So the fact that the layers in graphite are not bonded together makes it less constrained. So that means there can be more disorder or more entropy. So graphite has a larger standard molar entropy compared to diamond. Now, another factor is molecular complexity. So larger, more complex molecules generally have larger entropy. So for instance, let's say we're comparing argon gas to nitrogen monoxide gas. They have somewhat similar molar masses, although argon does have a larger molar mass. However, in this case, it's not molar mass that determines the standard entropy. It's the complexity of the molecules. So argon is just composed of single atoms, so not very complex, but then nitrogen monoxide has two atoms bonded together. So those two atoms create more complexity. So the standard molar entropy of nitrogen monoxide is greater than that of argon. And we'll look at some visuals on the next slide to kind of explain that further. Now, down below, we have two molecules that actually do have very, very similar molar masses, carbon monoxide and ethene, or C2H4. So their molar masses are about 28 grams per mole, but C2H4 has more atoms within its molecule compared to carbon monoxide. So C2H4 is more complex, which means that there are more energy states available, and so we can have more disorder or more dispersal of energy throughout. So the standard molar entropy of C2H4 is greater than that of carbon monoxide. Okay, so let's look at a visual comparing argon and nitrogen monoxide. So here we're showing nitrogen monoxide as a gas, and you'll notice that there are three types of motion that nitrogen monoxide can experience. It can experience translational motion, which means it's just moving around. Rotational motion, where it's rotating freely. And then vibrational motion, where the bonds or the atoms in the bond are kind of vibrating in different directions. So the bond can stretch, it can contract, whereas a single atom does have translational motion. A single atom like argon can move around. Rotational motion doesn't really have that much of an effect when you have just a single atom because the sphere will look the same regardless. But then vibrational motion, we don't have a bond in argon that will cause vibrational motion. This would more so be apparent if argon was in a solid state and it was vibrating. So nitrogen monoxide just has more, I guess you could say, energy dispersal, or ways that it can disperse its energy. And so therefore it has more disorder or more entropy. Okay, and then another factor that affects standard entropies is dissolution. So if we're comparing, let's say, potassium chlorate in its solid state to potassium chlorate dissolved in water, dissolved solids generally have larger entropy because the particles are distributed throughout a mixture. So aqueous potassium chlorate will have a greater standard molar entropy compared to just pure potassium chlorate in its solid state. Okay. So now that we kind of understand the relative standard entropies for different types of gases, liquids, solids, different complexities in our molecules, etc., let's talk about how we can actually calculate standard entropy change for a reaction. So the standard entropy change is the difference in absolute entropy between the reactants and products under standard conditions. So this must look very similar, hopefully, to our to the way that we can calculate a change in enthalpy for a reaction. So we take the sum of the standard molar entropies of the products, and we're also multiplying each of those standard molar entropies by the amount of moles of each product. And then we're going to subtract the sum of the standard molar entropies of the reactants, again multiplied by the number of moles. And then again, remember that although the standard enthalpy of formation of an element is 0, the absolute entropy of an element or a molecule is always positive, especially at temperatures above 0 Kelvin. Okay, so let's go over an example where we calculate the change in entropy for a reaction. And we're going to do that using these standard molar entropies. So I've included a few of those values below. And we're going to calculate the change in entropy for this reaction here, where 4 moles of ammonia react with 5 moles of oxygen to produce 4 moles of nitrogen monoxide and 6 moles of water in its gaseous state. All right, so the first thing we should probably do is find all of the standard molar entropy values for this reaction. So ammonia is a gas, so if we go to our gases column, it's in the middle there. So its value is 192.8 joules per mole Kelvin. And then oxygen gas is right below that. So we've got a value of 205.2. And then nitrogen monoxide is in one of the separate tables there. So its value is 210.8. And then gaseous water has a value of 188.8. Okay, so now we're going to plug that into our equation. And again, this is very similar to how we would calculate the enthalpy of a reaction. Okay, so let's rewrite our equation for delta S of a reaction. So we'll take the sum of the standard entropies of the products and multiply each of those by the number of moles. So we're going to take stoichiometry into account. And then we're going to subtract the sum of the standard molar entropies of the reactants. And again, we're going to multiply by the stoichiometry. So let's start with the products. So I'm going to put some brackets here. So nitrogen monoxide, we said, had a value of 210.8. but there are 4 moles of nitrogen monoxide. So we're going to multiply the standard molar entropy by 4. And we're going to add the standard molar entropy of gaseous water, but there are 6 moles of water here, so we'll multiply that by 6. And we said that the standard molar entropy was 188.8 joules per mole Kelvin. Okay, so that's our product, and then we're subtracting the reactants. So let's start with ammonia. There are 4 moles of ammonia, and the standard molar entropy of ammonia is 192.8 joules per mole Kelvin. And for oxygen, we have 5 moles, and the standard molar entropy is 205.2. Okay. So if we add and multiply, etc., all of the product values together, we get 1,976 joules per Kelvin. And then if we do the same for all of the reactants, we get 1,797.2 joules per Kelvin. Okay, so now if we add or subtract those two values, we should end up with 178.8 joules per Kelvin. All right. So not too bad, right? We're just kind of plugging in and calculating. Probably the hardest part is actually finding all of the standard molar entropies for these different molecules. Now, the change in entropy for this reaction is positive. And do we expect this to be positive? So if we look at our reaction, how many moles of reactants do we have and how many moles of products do we have? So we have 4 plus 5 moles of reactants, which is 9. And we have 4 plus 6 moles of products, which is 10. And remember that if we have more moles of product, that means we have more entropy. So we do expect that the entropy will increase for this reaction, so we should expect a positive entropy value. Okay, so now let's work on worksheet problem 7. So we're going to rank each set of substances in order of increasing standard molar entropy, and then we're going to explain our reasoning. So we're not going to look up the values for these different molecules. We're just going to use what we know about relative standard entropies. All right, so let's start with A, and it looks like we have all of the halogens there. So we've got iodine, fluorine, bromine, and chlorine. All right. So what factors should we consider here? Should we consider molecular complexity? Should we consider molar mass? Should we consider the states? So we have everything in the same state. They're all gases, so we won't consider that. In terms of molecular complexity, they're all diatomic molecules, so that's kind of out the window. So let's focus on molar mass. Which halogen has the greatest molar mass? And you can pause the video if you want to look it up. So you should find that iodine has the greatest molar mass. So it will have the greatest standard molar entropy. Now, we can rank these. So I2 would have a greater standard molar entropy than the next halogen, which has the next greatest molar mass. So that would be bromine. And then that would be followed by chlorine. And that would be followed by fluorine. So fluorine has the smallest molar mass, which means it has the smallest amount of entropy. So I2 has the greatest standard molar entropy, and fluorine has the smallest standard molar entropy. Okay. Now let's compare gaseous H2O, gaseous hydrogen peroxide, and then gaseous H2S. All right, so what should we consider here? Should we consider molar mass, the states, or the molecular complexity? So it looks like everything's in the same state, so we can rule that out as a factor. So molecular complexity might have something to do with it, but looking at these three molecules, they might also have different molar masses because they have different amounts and different types of atoms. So let's actually calculate the molar masses, or just kind of estimate the molar masses here. So H2O, we've got oxygen, which has a molar mass of 16, plus 2 hydrogens, which each have a molar mass of 1. So we have a molar mass of approximately 18 for water. For H2O2, we have 2 oxygens, so 16 times 2 is 32, plus 2 hydrogens, that would be approximately 34 grams per mole. And then for H2S, sulfur has a molar mass of 32, and if we add 2 hydrogens, we get approximately 34 grams per mole. Okay, so in terms of molar mass, we can see that water will have the smallest molar entropy. But we have a tie between hydrogen peroxide and H2S. Okay, so now let's consider molecular complexity. Which of those two molecules is more complex? So H2O2, right? Because there's 4 atoms present rather than just 3 in H2S. All right, so this would have greater molecular complexity compared to H2S. All right, so in our final ranking, we would put H2O2 as the or as having the greatest standard molar entropy, followed by H2S, followed by H2O. So again, we had to consider not only molar mass, but also molecular complexity for that one. All right, and then I'm going to have you do the last problem on your own. So in this problem, we're comparing graphite, diamond, and amorphous carbon. So you might have to do some investigating to figure out which of these has the greatest standard molar entropy and which one has the least or the smallest standard molar entropy. All right. Now next time we're going to talk about Gibbs free energy a little bit more, and we're going to see that there are 3 different ways to calculate Gibbs free energy. So I will see you in the next video.